And again, everybody say hello to Mike McKeon, our speaker. And please help me welcome our speaker for the morning. Astrophysicist Mike McKeon is a Ph.D. candidate in the Division of Geological and Planetary Sciences at Caltech. With 14 observing nights on the 200-inch telescope over the past 12 months, he has been working to characterize nearby Earth-sized exoplanets using the wide-field infrared camera on the 200-inch telescope. And he's been using that instrument to acquire precision exoplanet transit timings. Mike received his bachelor's degree in physics and astronomy in 2019 from the University of Maryland at College Park, where he was a Banneker Key Scholar and where, as I understand it, he played 2 winless seasons of intramural basketball. That's correct.
That's true.
I found that.
I don't know where you found that, but that's true.
While also completing his undergraduate program, Mike served as a space weather forecaster at NASA's Goddard Space Flight Center in nearby Greenbelt, Maryland. So we'll take questions at the end of the presentation. For that reason, right now, I'll ask everyone to turn off their microphones. Mike McKeon, again, welcome to the Greenway Talks online at Palomar Observatory. Thank you for taking time to speak with us today. And with that, please, the floor is yours.
Okay, awesome. Thank you very much for that introduction. Hi, everyone. Good morning. Thanks for coming. I'm going to just change my screen share here. I would also like to say that you may break the rules if you wish. You can unmute and interrupt me to ask a question if there's something that you'd like clarification on or a burning question that appears during the talk. That's okay. I'm fine with being interrupted. Otherwise, I'm happy to answer any questions that you may have at the end of the talk. Before I get into things, also, can everyone see my screen okay? Okay, great. Before I really get into things, I want to say just thanks to everyone for coming. And thanks to my advisor, Heather Knudsen, and my collaborators on this project, Shreyas Visapragada, Gautam Vasish, Renu Hu, and all the Palomar staff and the telescope operators and support astronomers who make these observations possible. Also, a quick note, the background here in the title slide, as well as my virtual background, is a beautiful shot of the 200-inch dome with the Milky Way in the background. This was taken by a summer student that I'm mentoring this year, Jorge Perez Gonzalez, who took this photo this Wednesday night when we were up at Palomar observing. Okay, so today I'm going to be talking to you all about how we can measure the bulk densities and compositions of small planets with the Hale telescope, which is an ongoing project that I have been working on in the past year, and it's a major part of my thesis. The story of this project can really be boiled down into 3 main questions, which are: how can we find nearby Earth-sized planets? What are these nearby small planets made of? And how do these planets evolve over time? As the talk goes on, it'll become clear how hard it is to answer questions 2 and 3, but these questions are all related to each other, and they involve areas of research which are actively and rapidly changing in recent years and right now. But we can use data from the Hale telescope to inform all of these big picture questions and more. And the fact that we can use a telescope which saw its first light more than 73 years ago to do cutting edge science and learn the properties of planets that are about the size of Earth around other stars in our solar neighborhood in our galaxy is really incredible. And it's something that I think the astronomers who first used this telescope in the 40s and 50s maybe never even thought would be possible. So let's get into the first question. How can we find nearby Earth-sized planets? And I'll say Earth-sized planets throughout this talk, but you should take it with a grain of salt. It's an approximate measure. Some of the planets are actually a little bit smaller than the Earth, and some, well, most of them are a little bit larger than the Earth. Most of these planets are between 0.8 and 3 Earth radii. And even in that small range of sizes between 1 and 3 Earth radii, there's a huge range of planetary diversity. So how can we find these nearby Earth-sized planets? There are a few ways to detect such planets, but the main method that I'm going to be talking about today is the transit method, because this is what's accessible to us with the Hale telescope. And the transit method relies on a fair bit of luck in the viewing geometry that we have to a certain star. It allows us to detect planets that pass in front of their host star relative to our point of view, which you can see a nice little video of here. Since it requires a bit of luck in the planet having to pass between the star and us, to find a lot of planets with this method, you need to look at a lot of stars and you need to look for a long amount of time. But if you can do that, if you can look at a lot of stars for a long time, eventually you will see dips in brightness that occur periodically, which correspond to planetary transits. And as you can see in this video, for a given star that has a certain size, the brightness as a function of time will have a larger dip for a larger planet and a smaller dip for a smaller planet. So what if we want to detect really small planets, planets that are around the size of Earth? Well, the dip in brightness is going to be really, really small. And in most cases, it's going to be undetectable from the ground, because as a relative change in flux from the star, Earth-sized planets for sun-like stars cause dips that are much smaller than 1 part in 1,000, which, given the typical photometric precision that we can achieve, is not really resolvable. So there's something that we can do that gives us an advantage in these observations and allows us to detect small planets more easily, and that is to look at small stars. So for a planet of a given size, say about the size of the Earth, if it transits a sun-like star, the dip in brightness will be relatively small, but if it transits a smaller star that's about half a solar radius, the dip in relative flux for that star is going to be larger. So you're going to hear me talk about M-dwarf stars a lot in this talk. M-dwarfs, also known as red dwarfs, are stars that are about 3,000 to 4,000 Kelvin, and they have sizes that range from about half the size of the sun down to around 1/10 of the size of the sun. They are the smallest main sequence stars, which are stars that are burning hydrogen to helium in their core. And they're also a very common outcome of star formation, and actually the most abundant stars in our galaxy. Most stars in the Milky Way are M-dwarfs. They're also fairly faint because they are so small, so they can be hard to observe. But when we can observe transits in planets, M-dwarf systems that host multiple planets, we can learn a lot about planets that are around the size of Earth, things that we couldn't learn for these same kinds of planets that might be around larger stars. So here's a really helpful diagram which explains how planets in these M-dwarf systems can be really fundamentally different from planets around sun-like or larger stars. These M-dwarf systems are really, really compact and are more comparable to the Galilean moon systems of Jupiter than they are to the terrestrial worlds of our own solar system. The size scale on the bottom here is log scale. So the difference in the distance of these planets to their host stars is an order of magnitude different from, say, the Earth to the Sun. So not only are these small planets around M dwarfs normally a lot closer into their host stars, but they're also normally much more compact systems. So the planets themselves are much closer to each other compared to our own solar system. And these stars are a lot smaller. Yes, you can see here TRAPPIST-1, which is about 1/10 the size of the Sun. And this is probably the most famous M dwarf planetary system. It's host to more terrestrial planets, though, than our own solar system. It has 7 approximately Earth-sized planets, whereas the Sun has 4. 3 of these planets are also in the habitable zone, which is the region where the equilibrium temperature of the planets could support liquid water. And the fact that this star has more terrestrial planets than our own solar system may not be a coincidence. So because the protoplanetary nebula that planets form in around M dwarfs has a lower mass, they are less likely to form gas giant planets like Jupiter. This is something that's also actively being debated right now, but it's thought to be probable that M dwarfs actually host more small Earth-sized planets because there are less gas giant planets to basically bully the planetesimals around and suck up all the matter before Earth-sized planets can form. So not only do M dwarfs provide a unique advantage for us to observe small planets, but they also provide more small planets for us to have the chance to detect in the first place. But how can we actually find these worlds? Well, the best opportunity that we have right now is the Tess mission. Tess, which stands for the Transiting Exoplanet Survey Satellite, is a satellite that has 4 CCD cameras, and it's in a highly elliptical orbit around the Earth, which is also a very stable orbit, and it'll be able to be in its current configuration for many years to come. The Tess mission has completed its primary and extended mission. It's been in space for a few years now, and it is an all-sky survey mission, which is a transiting planet hunter. So each of the cameras on the Tess satellite has a 24 by 24 degree field of view, and those camera fields of view are all stacked on top of each other. And the Tess satellite will observe one section of the sky, which you can see marked in blue here, for about a 1-month period, about 27 days. And then it will move on to another section of the sky. And over the course of 13 sections, or as we call them, sectors, which is about a year worth of time, it'll observe the entire northern ecliptic hemisphere. Then the satellite flips and it observes the entire southern ecliptic hemisphere. And it goes back and forth and it observes the whole sky over the course of years. You'll see that there's a lot of overlap with the sectors here at the top and bottom near the ecliptic poles, and that is no accident. The regions here where there's more sector overlap have more time for observations, and we're more likely to discover planets there. But those regions are also within the continuous viewing zone of the James Webb Space Telescope. So interesting planets which are discovered here, and planets are more likely to be discovered here in these regions that have a lot of observing time, they are amenable to follow up with JWST. So what do the detections look like so far from the Tess mission? Well, all of the gray dots in this plot are positions of stars on the sky that have confirmed planets. Most of these are transiting planet detections from the Kepler mission, from the Kepler Space Telescope. The blue dots are candidate planets from the prime portion of the Tess mission, and the orange dots are planet candidates from the extended mission. This plot is even a bit old at this point, but there are now over 6,000 planet candidates from the Tess mission, and a few hundred of them have been confirmed already, but it is going to take a lot of work to confirm the existence and the true planetary nature of the Tess candidates that have been revealed so far. So most of the 6,000 candidates that exist so far probably won't end up being real planets, but ground-based follow-up observations are a necessity for most of these candidates to confirm whether or not they are real planets. And the ground-based follow-up observations is where Palomar comes into play and the Hale telescope can shine. So if you look at the plot on the upper left over here, you can see a light curve, which shows the change in relative flux over time that is caused by a planet passing in front of the star from this planet, TOI 1749d. This plot is from the Tess mission itself, and the blue points are binned points from the Tess photometry. And in the bottom plot down here, you can see a light curve from the Muscat telescope, which is in the Canary Islands, in the Z-band, which is at wavelengths that are further to the red than the Tess bandpass. So it's important to observe these candidate planets at different wavelengths than they were originally discovered by the Tess mission, so we can be sure that the transit depth is not changing as a function of wavelength. If the transit depth is chromatic and it's different at different wavelengths, it's a sign that it's probably a blended eclipsing binary from a background eclipsing binary system whose light is blended with a foreground star, which diluted it and made us think that it's a tiny dip that could be a planet, but in reality, it's not. We also need to have adaptive optics imaging of the host stars in these systems to make sure that there are no background stars that are nearby that may have been blended in the test pixel or in our ground-based observation pixels that might be blended eclipsing binaries contaminating the light of the target star. And we also obtain spectra of the star to classify them. But one of the main things that's important in confirming the planetary nature of these candidate planets from the Tess mission are these kinds of ground-based follow-up observations at different wavelengths from the Tess mission to confirm that the transit is happening on the right target at the right time and it has the right transit depth. Okay, I see a question in the chat here. Could you identify which of these exoplanets might be able to observe an Earth transit in front of the sun? Yeah, you could. So if we know the position of the star in the sky pretty well, which we do thanks to the Gaia telescope, you could backtrack and see which of those systems have favorable viewing geometries to observe a transit of us in front of our own star. Unfortunately, unless there's an alien civilization on those other systems that has an incredibly powerful telescope, they probably wouldn't be able to observe a transit of the Earth in front of our own sun because the dip in brightness is really, really tiny. For example, this light curve shows a dip in brightness of about 0.02, so 2 parts per thousand. For Earth, it would be more like on the scale of parts per million. So nothing that we have currently on Earth could observe a transit of an Earth-like planet around a sun-like star from the ground. And any other system would have to have something better to be able to do that as well. Okay, so we can have ground-based transit observations as follow-up of these test candidates to confirm their planetary nature. And to do that, we need to have really precise light curves. Thankfully, the wide field infrared camera, also known as WIRC, on the Hale telescope, plus something called a beam shaping diffuser, which is an engineered component that we have in the filter wheel of the Hale telescope, gives us really precise measurements of stellar photometry, which I can illustrate here in this plot on the left. So these are all images of stars taken with work on the Hale telescope. And in the middle column here, we have the focused PSF of a star, PSF meaning point spread function, which is just the cropped out image of the star on the detector. And the rows represent different snapshots in time. So as you can see, even when we have the telescope focused optimally, the shape of the star on the detector is changing kind of significantly throughout the night. And this is because of variations in the Earth's atmosphere, from maybe changes in humidity or temperature or clouds passing by. And there's nothing really we can do about that for a focused PSF. something that some people do to try and stabilize the image of the star on the detector is defocusing. This works especially well for bright stars that might saturate the detector, but that we're still interested in observing transits of. But as you can see, the defocused PSF also changes significantly in time throughout the night. But when we use a beam shaping diffuser, which spreads out the light from the stars into a circular region that has kind of a top hat shape in brightness, you can see that the shape of the star is really stable over the course of the night. And here is a real image of that in the middle here for one of the target stars that we observed as part of the survey. Having the diffuser plus the large size of the 200-inch Hale telescope allows us to achieve a really good photometric precision in combination with the wide field of the imager, which allows us to have a lot of comparison stars. When we observe transits, we take a picture of the target star and the field around it around once every minute throughout the night so that we can track the brightness of the star. And typical brightness variations will be somewhere around tens of % throughout the night due to changing atmospheric conditions. But the transit signal that we want to catch is much, much smaller. It's like 0.01% compared to tens of %. So if we can track how the brightnesses of all the comparison stars in the field are changing, which will all change in a similar way because they're experiencing the same atmospheric fluctuations, we can remove those long-term trends from the light curve and get just the tiny signal that corresponds to the transit. And work does a pretty great job at this. Here's an example where on the right, there's a panel from the Kepler Space Telescope, which observed the transit of this planet that has gray points showing the typical precision in the photometry. And the two images on the left are sample observations that we obtained with work on the Hale telescope. And you can see that the scatter in the gray points is only about 2 times as large as the Kepler Space Telescope, which is really impressive to get nearly space quality photometric precision for a ground-based telescope. Another question in the chat here is, for clarification, most TESS observations will be at the poles because of the overlap of time on segments. Are there any other factors to influence planetary discovery, such as density of populations? Yeah, so most of the TESS discoveries are at the poles. Well, not most, but there is a preference for discovering planets at longer orbital periods near the poles because they have more time in that area. But if a planet has an orbital period that's less than 1 sector of TESS observations, if it's less than 27 days, we can have a higher chance of observing it in just maybe 1 or 2 or 3 sectors. If a planet has a really long orbital period, say hundreds of days, there's no chance really that we can observe it down here near the ecliptic equator because there's not going to be that many TESS observations in the first place, and the odds that the transits line up in the exact periods of time when we have TESS photometry are going to be lower. There are preferences for the locations of planets on sky, just because when we look within the galactic plane, we're more likely to see planet hosting stars, but those aren't incorporated into the biases of these TESS field pointings. Okay, so we can obtain really awesome precise photometry with work that's comparable to even the Kepler Space Telescope photometry, but the TESS photometry is not actually based on telescope observations. TESS just has 4 cameras. They're CCDs really that are pointed at the sky. So the TESS observing precision is a lot worse than Kepler. As you can see here in this plot, I have 6 sectors of TESS observations. So about 6 months of continuous space-based photometry from the Tess mission for this particular planet candidate. And the black points are the binned data in the light curve to a bin width of 10 minutes. And you can see on the bottom here, we have the plot of work photometry for just 1 night of observation from Palomar earlier this year. And in 1 night on the 200-inch, we can get more precise photometry for this planet candidate than all 6 sectors of TESS observations, which is really impressive and awesome because it means that we can improve our information on the transit shape parameters, which include the size of the planet, so its radius, as well as its orbital parameters like the orbital period and semi-major axis. And not only can we improve our knowledge of the planetary parameters by getting more precise photometry like this, and we can confirm the planetary nature of these objects, but we can also get really precise transit timings, which I'll explain the importance of in just a few slides. But after that, which explains how we can do follow-up based on initial discoveries by the Tess mission to confirm planet candidates, we can talk about what these newly discovered planets might be made of. So before we talk about the composition of these small Earth-ish sized planets, it's important to discuss what we know about this kind of planet from the Kepler mission. So this plot illustrates one of the main results from the Kepler mission, which has to do with planets that are smaller than about 4 Earth radii. And you can see on the x-axis here, they range in orbital period from 1 to 300 days. Kepler discovered thousands of transiting planets, and hundreds of them are in this parameter space. But you can see that they're not evenly distributed around orbital period planet size space. There's a clump of a lot of planets that are smaller than about 1.5 Earth radii. And then there's not a lot of planets that are around 2 Earth radii. And then there's a ton of planets that are clumped together above about 2.2 Earth radii. Now, this is not a coincidence, and it was actually something that was predicted about the population of exoplanets before this result even came down from the Kepler mission. It was theorized by astronomers that irradiation from the host star would be important in shaping the evolution of these small planets. And planets that start up here in this regime, which we call sub-Neptunes, that are consistent with a composition of a rocky core surrounded by a hydrogen and helium-rich atmosphere, as they're irradiated by their host star over time, the radiation will blast away the atmosphere and sculpt these planets down as they transition to bare rocky cores that lack a significant volatile-rich atmosphere. So this evaporation valley is called an evaporation valley because it may be caused by the atmospheres of these planets evaporating under radiation from their host stars. There are other explanations that might explain this radius valley between sub-Neptune and super-Earth planets, like core-powered mass loss, which theorizes that the residual heat of planet formation can heat the atmosphere from the inside out and blow away the outer layers over time, which can also result in a valley between these sub-Neptune and super-Earth planets. And right now, this Kepler result pertains to planets that are around sun-like stars and stars of similar sizes to the sun. Because M-dwarf stars are so faint, the Kepler mission did not observe planets around very many M-dwarf stars. It didn't have that many detections around these small stars. So this result only really applies to F, G, and K type stars, which are larger than M-dwarfs, and we think might have some fundamentally different properties. So how might this picture change for small planets that are around M-dwarfs? Well, so far, we only have about 40 planets that are smaller than 3 Earth radii in this regime for M-dwarfs that have well-detected radii and masses. You'll notice in the previous plot that I didn't talk about mass information here because we don't need it. There are so many planets that we can clearly see the groupings of a lot of sub-Neptunes, then not many planets in between, and then a lot of super-Earths. But for M-dwarfs, we need to incorporate extra information because there are much fewer planets in this regime that we know of so far. to try and discern whether a similar thing with the radius valley might be happening here. You can see by the color coding in the plot on the left that the blue points are marked as subneptunes. So these are rocky planets that have a significant hydrogen helium atmosphere. And then the brown planets down here are super Earth planets. And there's a fit through the middle here that's labeled as M dwarf valley. But this result is very much questioned right now. It's not necessarily clear if there is a radius valley at all for M dwarfs, and if there is, what its slope might be. The slope of this valley has to do with how aggressively photoevaporation might be happening, or if there's no slope to the radius valley, it could be a sign that there is inherently different compositional differences in these small planets. It's theorized that small planets around M dwarfs might be more likely to host a lot of water. And if you look in the plot on the right here, which is in mass radius space, you can see that there are composition curves plotted, which are consistent with a given density that we can calculate from a planet's mass and radius. The brown lines down here correspond to pure rock compositions or Earth-like rocky or mixtures of half rock and half iron. And based on the uncertainties in these measurements, we're pretty sure that these planets are consistent with some kind of rock metal mixture that doesn't require a large atmosphere as a fraction of the total mass of the planet. Whereas these sub-Neptune planets up here are consistent with either an Earth-like rocky composition plus 1 to 2% hydrogen helium atmosphere, or this blue line here, which is a pure water composition. So there's some overlap in the potential compositions of these planets that are consistent with the mass and radii measurements that we have so far, where they could be sub-Neptune planets that are rocky worlds with hydrogen atmospheres, or they could be water worlds, which are rocky with a huge amount of water, way more water than we might expect from the amount of water that's on Earth in our terrestrial oceans. I have another message in the chat here. Is it possible over time to get Tess into a new stable orbit with a 90-degree shift of overlapping views? I don't actually know. I think it would probably be difficult because there's only so much fuel on the satellite, and most of it was spent getting it into its current stable orbit. But there's not much fuel that's needed to maintain the current orbit of Tess. And it's so stable that it can go for many years to come. So if the Tess mission goes on for 10 years or so, and we think there's not a whole lot more that we can get out of it, it might be an interesting possibility to use whatever fuel remains to change it into a new configuration that has more time spent on the neglected regions of the sky that haven't been observed at a higher cadence with the current Tess mission. But yeah, I'm not sure about that. An interesting idea. Okay, so we're not really sure what the compositions of a lot of these small planets around M dwarfs might be, and we're not sure if a radius valley exists for M dwarfs yet. But one thing that's complicating this picture is how much water these M dwarf planets might have. And people think that there might be a lot more water around M dwarfs because of something called the frost line, also known as the snow line or the water ice line. Basically, the protoplanetary disk, the disk of gas and dust that these planets form out of right after the star forms, has a range of temperatures. And as you get further away from the host star, it gets colder and colder. And at some point, it gets cold enough for water to condense into ice. Closer than that line, the water is vaporized, and beyond that line, it exists in solid form as ice. And planets that form outside the frost line will have a lot more water content than planets that form inside that line. Because M dwarfs are much cooler in temperature than sun-like stars, their frost line is a lot closer into the star. And we think that because of that, M dwarf planets might have a much higher water content because they form outside that frost line, and then they either migrate in closer to their host star where we currently observe them, or they hover around that region where they can accrete a lot more water than the terrestrial worlds of our own solar system. Some simulations of planet formation around M dwarfs seem to confirm this theory. The dots here are the result of planet formation simulations in M dwarf protoplanetary disks, where they're color coded as a function of their water fraction. So for reference, the Earth's water fraction by mass is about 5%. So anything that's even a little pink or towards the blue in this plot has many, many times the total amount of water than what Earth has. And you can see a lot of the planets that come from planet formation around M dwarfs have a lot of water. So we might expect there to be a lot of water worlds amongst the small Earth-ish sized planets around M dwarfs. The water droplets here represent the range of orbital distances from a typical M dwarf host star where the water would be heated up into liquid form. Okay, so M dwarfs could have a wide range of compositions, and we're not really sure what they are yet. How can we actually measure what these planets are made of? Well, we have to determine their masses and radii, so we know their densities and therefore what bulk composition is consistent with that density. And one way that we can measure those masses and radii is through transit timing variations. So when planets are in multi-planet systems, they will have transit midtimes that deviate from constant periodicity. And in this video here, you can see that when there's one planet in the system on a circular orbit around its star, the transits come at perfectly regular intervals, exactly equal to the orbital period of that planet. But when there's another planet in the system, which I will skip ahead to here, the planets are tugging on each other gravitationally. When they're closer together, they pull each other more strongly, and when they're further apart, they pull each other more weakly. But the result is multi-planet systems that have orbital period ratios that are close to some key values show deviations in the transit times of the planets. So they're no longer passing in front of the star at the regular intervals that we would expect from constant periodicity. And the way that we can get measurements of these transit timing variations is when planets have adjacent planet pairs that are close to first order resonances. This is what happens when you have orbital period values that are close to integer ratios. So like 2:1 or 3:2 or 4:3. So like a planet at 10 days and then another planet at 20 days. And if they're close to those resonances and planets are both transiting, we can detect the variations. This plot on the right shows the transit timing variation in minutes as a function of time for one system that we observed with work over the last couple of years, which we recently published. And you can see the transit times are varying quite a lot on the scale of hours. By modeling the gravitational perturbations between these planets, we can retrieve the masses of the objects because we know how much they should be tugging on each other, and we know what we can backtrack and figure out what mass that corresponds to. We know the radii of the planets already because they're transiting. And once we have that additional mass information, we can know their density and bulk composition. So how many planets can we actually characterize in this way for M dwarfs, right? Because we need to have multi-planet systems, and we need to have multiple planets in that same system that are all transiting. And we need to have those multiple planets in those systems be close to orbital resonances with each other. So it's a lot of limitations that go into this, but Tess discovers so many planets that there are actually a bunch of systems that are great for characterizing the masses of these small Earth-sized planets with TTVs. On the left, you can see a plot in orbital period radius space with black stars marking all the planets that are part of our survey that we're doing with the Hale telescope to measure the masses of these planets. There are a lot of potentially rocky Earth-like planets, and there are also quite a few potentially gaseous sub-Neptune planets that we are observing over the past year and will be observing over the next year to try and measure the masses and composition of these planets with transit timing variations. Right now, these black points on the right are just placed on theoretical values from composition curves, but eventually we will know the real locations of these planets in this plot, and we'll be able to tell what their likely compositions are. Okay, I'm going to go to this slide now, which shows just how much our Hale telescope observations can improve the measurements of transit timing variations. So here is an example system, which we started this survey observation with. And you can see the red stars are the 2 planets that are in this system. They are near the 2-to-1 orbital resonance. And the inner planet in this system is a small planet that is probably a rocky sub-Neptune, if we believe the conventional picture of the radius valley from the Kepler result, while the larger planet is on the larger side of the radius valley. So if we believe the conventional picture, it should be consistent with a sub-Neptune composition that has something like a 1 to 2% by mass atmospheric fraction. Okay, I see a question here in the chat. Candidate 2095.02 is really close to the center line of the evaporation valley. What are possible consequences / explanations for this? Yeah, so that planet is a really interesting one because both of these planets are actually kind of close to the evaporation valley. So I marked this radius valley with a dashed line, but you'll notice I put a question mark on it because we don't know the real location of this for M dwarfs yet. There are so few planets in this parameter space that you could really move this line kind of up or down, or you could tilt the angle of it, and it would still be mostly consistent with the data that we have so far. And the location and slope of that line is probably going to change significantly as we add more planets to this list. So what the actual real composition of TOI 2095.01 and 2095.02 are is going to inform the true location of this line. If both of these planets turn out to be rocky sub-Neptune planets, then we know that this line should actually probably be further up. But if maybe one of them is more rocky and one of them is consistent with having a larger atmosphere, that's going to be confusing, and it might be consistent with this line having no slope at all. So the planets that are closest to the evaporation valley, like 1266c, the 2095 planets, 1749b, those are going to provide really a wealth of information about what is going on in this population of planets and whether or not M dwarfs follow the same population trends as what we know about the larger stars from Kepler. And we're really just beginning to start to learn about the results from this survey. We've observed a few of these systems so far. We're not completely finished on observations for any of these systems yet, but we're nearing completion for 3 of them. One of them is this system, TOI 2096. And as you can see, like I was saying before, it straddles the proposed location for the evaporation valley. And if you look in the plot on the right, the gray points are transit timing points just from Tess data alone. And the blue model is the best fit model for the TTV solution using only the Tess data. And as you can see, it's pretty uninformative. It just kind of randomly goes through all the data. But when we add the black points, which are our Palomar observations, the timing precision that we can achieve is way better than Tess. The typical Tess precision for this particular planetary system for a single transit is somewhere between 10 or 20 or maybe even 30 to 40 minute timing uncertainty per transit. Whereas with the Hale telescope and work, we can achieve a timing precision around 1 minute or less. So it's a drastic improvement in the timing precision. And because of that, we have a drastic improvement in the TTV model. You can see the red model, which incorporates the Palomar data, really snaps down to the true solution once we add our Hale observations. And the result of this improved timing precision and improved model for the transit timing variations is we get better bulk composition constraints. So in this plot, in planetary mass radius space, we can see some preliminary results from our observations of TOI 2096, where the blue points are the constraints on the planetary mass and radius from the Tess mission alone, and the red points are when we incorporate our Palomar data. These results are preliminary. We're not done observing the system yet, and there are some improvements that we can make to our analysis of the light curves. So not final results, but it appears that the outer planet 2096.02 is consistent with an Earth-like rocky composition plus a small fraction by total mass of hydrogen atmosphere. And it appears that the inner planet is consistent with an Earth-like rocky composition, or maybe a significant water fraction water world, but it probably doesn't have a large atmosphere. And this result is actually consistent with what we would expect from the Kepler result for small planets around larger stars. So the planet that is around 1.5 Earth radius is consistent with having a super Earth composition, and the planet that's around 2.1 Earth radius is consistent with a sub-Neptune composition. This is only the first system in our survey though, and we're going to get results just like this for several other systems really soon. So I don't think they're all going to confirm this similar picture of small planet compositions from Kepler, and I'm going to be really interested in digging into the confusing ones. Here's an example of some of the other light curves that we've obtained so far in the past few months as part of our survey, and we're going to have more results coming soon. So now that we talked about how we can constrain the masses and compositions of these planets, I want to briefly touch on how we can think about the evolution of these planets over time, particularly how their atmospheres might change over time. One thing that's theorized to be important about the evolution of these planets from sub-Neptunes to super-Earths is atmospheric mass loss, which can transform a planet from something like this that has a large gaseous envelope over time getting blown away down into a bare core. This process depends on the luminosity of the host star, how active it is, how often it might be flaring and depositing energy into the planetary atmosphere. And the systems that we're observing as part of this survey with Palomar include some M dwarfs that have a high level of activity, which is probably really important for these small planets around small stars. M dwarfs have larger flares than sun-like stars, both in total energy and as a function of the relative flux change. They flare a lot more frequently than sun-like stars, and they flare for a longer part of their lifetime. So these smaller stars are a lot more active, and they might be depositing a lot more energy in the atmospheres of these small planets. So it's reasonable to expect that when we look at the sub-Neptune planets around M dwarfs, their atmospheres might be being sculpted in a much more vigorous way than the same kinds of planets around sun-like stars. On the left here is a plot of only about 7 days of observation of one M dwarf in Tess. And you can see a couple flares that change the total brightness of the star by a few percent just in that 7-day timescale. These flares are huge compared to flares that we see on the sun. And then on the right, you can see a color magnitude diagram of all the stars that are observed in a few representative test sectors, with only the stars that are flaring marked as red. And you can see most of the stars that are flaring are to the right of the M0 line, meaning most of the flaring stars are M dwarfs. One of these such flaring M dwarf stars is actually part of our survey. So this system is TOI 2267, and the plot on the left shows the photometry of this star, which has a rotation period of 0.7 days. So this star is absolutely spinning super rapidly, and it's also incredibly active, probably because the fast rotation period is tangling up the magnetic field lines of the star, and those magnetic field lines are eventually breaking and releasing their energy in the form of flares. On the right, you can see a flare from this star, which takes the relative flux from 1.0 all the way to 1.9. So just a huge increase in the total brightness of the star from this flare. And this star has 2 planets around it, one with an orbital period of 2 days and one with an orbital period of 3 days. And we are going to observe transit timing variations in those planets and figure out their compositions. And I'll be really interested to see what the results are, because if these planets have large atmospheric mass fractions, it will suggest something about the efficiency with which these active M dwarf stars can strip atmospheres from close-in planets that orbit them. These observations are coming up this year. Starting in August, we'll be observing the system until February of next year. And one final thing that I want to mention is a very interesting system that we have been observing for the past 5 months or so, and we will be observing again in the next few months, TOI 1266, which has one planet which is 2.4 Earth radius in size, and another planet that's 1.6 Earth radius in size. But the typical order that we'd expect them to be orbiting the star is flipped. So the small planet, TOI 1266 C, is actually the outer planet, and the large planet, TOI 1266 B, is the inner planet. Normally, we would expect the rocky super-Earth to be closer into the star because it's receiving more irradiation from the host star and its atmosphere is more likely to be lost. And we'd expect the larger sub-Neptune planet to be further away because it's safer from the radiation of the host star out there. But in this system, that convention is flipped. And the larger sub-Neptune planet is closer to the host star, while the smaller super-Earth planet is further out. There are some preliminary constraints on the composition of these planets from test data and some other ground-based follow-up, but the mass measurements aren't precise enough for us to really be sure about the composition of these planets. And the inner planet could be consistent with Earth-like rocky, it could be a water world, or it could actually have some small hydrogen fraction in the atmosphere. And our observations are going to shrink down these error bars by a ton. And once we incorporate the Palomar data, we're going to have a really good idea what the composition of these planets are. And I think it may be confusing for the typical narrative of sub-Neptune to super-Earth composition. So with that, I'll just do a brief recap and say that multi-planet near-resonant M-dwarf systems provide a really unique opportunity for us to study the characteristics of small Earth-sized planets. And we're doing a survey of these systems with Palomar that's going to help us understand the demographics of these worlds. And it'll also help us understand how atmospheric mass loss can affect these small planets. With that, I'll take any questions now.
Well, Mike Greklek-McKeon, that is marvelous. That I'm amazed that this can be done, that this information can be obtained. And thank you very much for the presentation. Everybody, questions, please turn on your microphones and step in.
Okay, I'll start with one. What is your observing routine for a night at Palomar? I noticed some of your observations of a rapid transit seem to be fairly short. So are you dwelling on a star, taking a bunch of short images for reduction to photometry later, and then going to other stars, or just how do you go about it?
Yeah, that's a good question. And it depends kind of on the target and on the night. For the most part, these planetary transits are between like 1 to 3 hours. And we can't just observe the transit. We also need some baseline so that we know what the relative flux difference is. And typically we try and get about 1 transit duration worth of baseline. So if a transit is 2 hours in duration, we might slew to the target an hour before the transit starts, start taking continuous images, go through the end of the transit, plus another hour or 2 at the end after that. And then that's enough data really for us to get a precise measurement of the transit depth and transit time. So if that only takes 5 hours and we have 5 more hours in the night, we will try and go to another target and observe another transit. Some of the nights are shorter, some of the transits are longer. So usually we only end up being able to observe 1 transit per night. But when we can, we try and squeeze in as many transits into one night as we can. There is a couple questions in the chat. I we'll read one of them here. What are the odds these planets have a magnetic field that shields them from the flares?
Oh, good.
That is an interesting question, and we really don't know. But based on what we know from our own solar system, I mean, the Earth currently has a magnetic field. Mars had a magnetic field in its past, we are pretty sure. Mercury and Venus don't have very strong magnetic fields, but 2 out of 4 ain't bad. So the odds that these small planets around other stars have magnetic fields is decent. It's probable that some of them will, and we may be able to learn something about the magnetic properties of these planets based on whether or not they're able to retain their atmospheres, especially for these really active host stars that have these small planets that are really close in. We can actually calculate the expected atmospheric mass loss for a planet if we know its atmospheric mass fraction and we know the spectrum of the star and how often it flares and what those flare energies are. So if we detect a planet that is really close to the host star that we know is getting blasted by a lot of radiation, and our calculations show that it should have lost its atmosphere in the age of the system, but it hasn't, and we still observe an atmosphere on that planet, that might be kind of indirect evidence that the planet has something that's defending its atmosphere, like a magnetic field. Yeah, that's potentially a really exciting avenue to explore.
There was a colleague of mine at JPL who was looking for planetary magnetic fields around other stars using radio to look for synchrotron emission. But it seems to me that around a magnetically active star like most dwarfs, you'd probably be dwarfed by the signal from the star and you kind of miss it.
Yeah, so another project that's part of my thesis that I'm actually involved in is a joint optical radio search for space weather signatures from other stars. So we have some observations with the Owens Valley Radio Observatory with the long wavelength array that coincide with Tess observations. And we can actually observe flares in the Tess photometry in white light at the same time as we have low frequency radio observations, which could potentially hold signatures of like type 3 and type 2 bursts, which correspond to coronal mass ejections from our sun. So we're working on a project that does a search in the radio for the radio signatures of the shock front of a coronal mass ejection propagating through interplanetary space at the same time that we know a flare happened. And if there are planets in those systems, it is possible that you can get like electron cyclotron maser emission from the auroral signature of the interaction between the planet and the star. And we could potentially observe in the radio a signature like that if the planet is magnetized or conductive and the magnetic field configuration of the star is just right. Yeah, that's something that the people at Owens Valley are working diligently on. And TOI 2267, which is the active star that I mentioned earlier, is actually one of the targets for OVRO, or it's going to be one of the targets that we look at in the radio. So yeah.
Can you discern small close orbital double planets from a regular planet in the survey or in the study?
What do you mean by double planets?
Well, like Earth Moon, for example. Imagine there's a system like Earth Moon that goes around. Is that possible to discern that from the rest of the planets that turn around the system, or is that not possible? Because I can imagine these distances are much, much shorter.
Yeah. So actually, if there was a system that was like the Earth Moon, we would actually be able to tell the transit timing variations within that Earth Moon system as being separate from transit timing variations caused by 2 planets around a star that are further from each other. That would be a really different signal that would manifest in the photometry. That's something that people have actually done to search for exomoons. They've looked at transit timing variations of planets to indirectly detect if there is a moon orbiting the planet. That would be a really weird signature if we did get it, and rare, but in theory, yeah, we'd be able to tell the difference.
Thank you.
This is a fascinating talk. But in terms of planetary or rocky planet development, is it fair to say or safe to say that rocks are rocks? For example, you could have a different mixture of silicate rocks versus, iron rocks and so forth that would give you a different mass. So is there some initial condition that would cause the variation, or is it okay just say, we know what rocks are?
Yeah, well, right now we're just saying, rocks are rocks, and it's probably like iron core with a silicate mantle. But we're only saying that because that's all we can say right now. These are really crude measurements, right? All we have really is a measurement of the total planetary mass and the total planetary radius, which gives us the whole density of the planet, the bulk density. And there's not a whole lot we can say about the specific composition of a planet from just the bulk density. And there are different combinations of different kinds of rocks and different kinds of metals, which are all plausible components of the building blocks of a planet. And right now, we can't really distinguish with high confidence what those differences are just based on the bulk density measurements. So for now, we know that the planets in our own solar system are mostly silicate rock mantles around mostly iron cores. And that's how we're interpreting the data that we have for exoplanets. But we don't really have any proof that that's the true composition of these other worlds. Yeah.
Thank you.
Mike, there are a couple of questions, again, from the chat. Grant asks, have you ever lost a transit due to a flare from an M-dwarf star?
Yeah, so not yet, but I fear that day is coming, especially when we start our observations of that active star, TOI 2267. That star actually flares about once every 2 days, so like once every 48 hours. And our observations that are scheduled for that system, we have about 35 hours of time on that system coming up. So if there's one flare every 48 hours, and we have 35 hours of time on it coming up, there's a decent chance that there's going to be a flare that might contaminate that. So it's something that we've thought about and that will probably happen eventually, but not yet. If it does happen, though, it's not necessarily a bad thing. We can model the flare profile and calculate the energy of the event in infrared wavelengths, which provides additional information to the TESS observations of flares, which are in optical wavelengths. So we'll still get some useful science out of that.
And Manny has asked, how do these exoplanets gain their atmospheres in the first place if the M dwarfs have flares that would have prevented any atmosphere from forming?
Yeah, so that's a good question. And it's a common outcome of planet formation is having some degree of hydrogen helium envelope, just because the protoplanetary disk that these planets form out of is just chock full of hydrogen helium. And as long as you have enough mass to form a spheroid and the planetesimals combine to have a high enough mass to get a planet in the first place, you're gonna accrete some amount of hydrogen and helium just because of the gravitational potential of the planet and the fact that it's everywhere in the protoplanetary nebula. For the most close in planets around these M dwarfs, if they're really active, we might expect them to lose that atmosphere really quickly. But while the gas is still in the protoplanetary disk, there's a lot of damping that's going on from the stellar flares. So after some millions of years, the gas in the protoplanetary disk will eventually dissipate, and then the atmospheres will become vulnerable to atmospheric mass loss from flares. But before that time, while the protoplanetary disk is still full of hydrogen and helium, the atmospheres are less vulnerable because there's a lot more stuff in the way between the star and the planet that can absorb the energy of those flares.
Remarkable, remarkable. Going on down the list here, Mark has asked, how best can citizen science or citizen scientists support your efforts? And is there a point, is there a way for citizen scientists to get involved?
Yeah, so I see a reply to this comment from John saying, take a look at Exoplanet Watch, and that's a good suggestion. Yeah, so the Tess has a follow-up program for ground-based follow-up of these candidates, and citizen scientists are a big part of that. I am part of the Tess follow-up program working group 1, which is ground-based follow-up of transits for Tess candidates, and I use the 200-inch telescope for that. But anyone that has a telescope that's capable of achieving the required precision to observe these transits can contribute data that helps confirm or deny the planetary nature of these test candidates. You need to have a pretty good setup to observe these specific kind of planets that I talked about today, just because the transits are so shallow. They're like 1 part in 1,000. But there are larger planets discovered by Tess. There are Jupiter-like planets that are very close to their host stars that have transit depths on the scale of several percent, which is something that's achievable for small telescopes from the ground to observe. So there are citizen scientists that contribute light curves to the Tess follow-up program with ground-based observations. And there are so many candidates, we could use help. We do need a lot of people to follow up these thousands of candidates and clear the field of nearby eclipsing binaries and check the timing of these transits to refine the orbital ephemeris and to see if the transit has a different depth at different wavelengths. So it's going to take a lot of work to observe all these candidates, and anybody that can get a precision of maybe a few percent or better on the relative flux of a given star throughout the night has something to offer, and we could really use the help.
Other questions?
I'm curious about the atmosphere loss mechanism. As I recall, in the aftermath of the discovery of the hot Jupiters, simulations that were then done, because nobody had done it before, showed they could hold on to their atmospheres rather better than people expected. So do you have hydrodynamic simulations of the loss mechanism? Maybe the flares don't throw away the atmosphere as readily as you might think.
Yeah, so this has kind of been a subject of back and forth discussion within the last few years, where some studies calculate what's called the energy limited mass loss from flares deposited in these planetary atmospheres, where they basically calculate like the total X-ray energy that's deposited for a given flare and see how much it heats the atmosphere and how much mass that's likely to kick away. And then they look at the activity for a given star and calculate how much mass loss we expect over time. And some of those studies predict that these close-in planets should lose most of their atmospheres really quickly, while others predict that the atmospheres should be stable. And likewise, like you said, there are hydrodynamic simulations of these as well, which also try and incorporate the solar wind into the equation, because it's not just flares that are stripping the atmospheres. The ambient solar wind over time for even these closest planets can also play an important role in heating these atmospheres and removing mass. But unfortunately, it depends on a lot of unknown factors that are currently unconstrained for these planets, like whether they have magnetic fields or not, and also the composition of these atmospheres. If the atmospheres are completely made of hydrogen and helium, they're really light and it's easier for them to be puffed up and blown away. But if the atmospheres have a higher mean molecular weight, maybe because there's more water content in these planets and there's a lot of steam in the atmosphere, or maybe because of outgassing of heavier molecules, that will add to the weight of the atmosphere and make it easier for the planet to retain over time. Unfortunately, right now, we don't really know the composition of these atmospheres, but it's something that we're going to start learning soon from James Webb Space Telescope observations. The system that I showed in the beginning of the talk, TRAPPIST-1, has scheduled observations with James Webb Space Telescope that are going to take spectra of the atmospheres of some of the planets in that system. And yeah, hopefully that'll give us a better idea of what the atmospheres are made of, and that'll inform our knowledge of how they might be stripped or might not be stripped over time.
And Curtis has asked, might not these planets have volcanoes or tectonic fissures that outgas and replenish their atmospheres?
Yeah, so that's an interesting idea as well, which a lot of people have thought about, and it's particularly relevant for the types of planets that I'm working on in this survey with transit timing variations, because it's possible that planets could have a lot of residual heat from their formation. So when the planets are young, they could have a lot of volcanic activity, which would, I'm sure, involve outgassing that contributes to their atmosphere. But over time, that residual heat from formation is going to go down and the planets will cool. So you need some force to replenish the internal heat of the planet to maintain that volcanism over time and replenish the atmosphere on the scale of hundreds of millions to billions of years. And one of the best ways to do that is with tidal forces. This is what drives the volcanism of Io, one of Jupiter's moons in our own solar system. The Galilean moons around Jupiter are close to orbital resonances in the same way as these systems that exhibit transit timing variations are close to orbital resonances. And the gravitational tug between the adjacent moons and Jupiter creates heat inside the planet because of these tidal interactions, which drives the volcanism over long timescales. And it is entirely possible that some of these planets could have similar effects, especially if there are adjacent planets next to each other that are very different masses, like one is low mass and one is high mass. And then both of those planets are also very close to the host star. The tidal forces are supposed to be really high. So it's possible that for a planet like that, not only could it have volcanoes that might outgas and replenish the atmosphere, but it could also be so heated that it's basically a magma planet. The whole surface of the world could be lava, and yeah, it's just like a lava world or a magma planet that has no solid surface. So yeah, that's a really interesting possibility. And there are a few candidate planets that have been detected that seem to be consistent with that kind of composition, but we don't have any atmospheric measurements of those planets yet. Thanks for all the awesome questions. These are all really interesting topics.
Well, and Mike, thank you very much for your time. Been very generous with your time today, and we're running almost hour and a half. Let me ask if there is one more question we could take before we close the meeting. Anybody else? Anybody else have a question? If I could, I'd like to find out. I have heard the term diffuser associated with work before. Can you help me with this? What is it? What does it do? How does it operate? Because no one here has ever explained it to me. Of course, I've never tried it.
It's kind of like magic for us in terms of giving us a nice stellar PSF on the detector, but the formal term for what we have placed in the filter wheel is a custom engineered beam shaping diffuser. And what it is a piece of glass that has very carefully sculpted bumps on it. And the height of the bumps and their separation is what determines the diffusion of the stellar PSFs. And these are really tiny bumps that are very expensive to manufacture because we want the PSF of every star in the image to be diffused. So all the light coming in at any point across the diffuser, which is basically just like a normal filter that it's clear, it should have 100% transmission but it just has these bumps on top of it, which scatter the incoming photons and spread them out into a nice shape. And yeah, the height and size distribution and spacing of the bumps is what determines the diffusion angle of the PSF for the stars.
Okay, that kind of makes sense to me. Anyway, thank you very much for that. And thank you very much for the presentation and the discussion. Again, it's amazing that we can know all this. As you pointed out, it's amazing that we can do all this on this old telescope. The people who built it were sure that if exoplanets existed, we'd never be able to see them. And it's amazing that we are doing with telescope they did, we are doing what they thought would forever be impossible. I think it's an amazing thing. Anyway, I think we need to wind the meeting down. Let me finish off with a note about our next meeting. The Greenway Talks online will continue on Saturday, August 6th. Professor Meg Urey is the Israel Munson Professor of Physics and Astronomy and Director of the Center for Astronomy and Astrophysics at Yale University. Her research focuses on active galaxies and the accreting supermassive black holes they host at their centers. She will discuss her work in a presentation titled Black Holes, Galaxies, and the Evolution of the Universe. So again, thank you to Mike Greklek-McKeon, and my thanks to all of you for attending and supporting the Greenway Talks online. With that, I'll bring the meeting to a close, wave goodbye, please stay well, and we'll see you on August 6th. Thank you, everybody.